Okay. So all in all, what's wrong is we don't know what V final is in this number 11. You're given 1 mole of water. You're also given density of 0.996 grams per milliliter, or per centimeter cubed, which is per milliliter. So let's just go ahead and exchange that now. And you're given V final of 30.6 liters. So what did you guys do here? Those of you got it. Sean. Okay, so 1 mole of water is 18 grams of water per 1 mole times 0.996 grams in the bottom and 1 milliliter on top. So what did you get for your milliliters? And that is V final, right? But V final and V initial have to be in the same unit, so then you would just convert that to 0.0186 liters. 0.0186 liters, and then find your delta V. That, and all in all, what units are going to be present for work after you're done calculating? Atmosphere liters, and to get from atmosphere liters to a usable form of energy, what's the conversion? 101.3 joules per, I thought I said kilopascals, joules per atmosphere liter. And then joules have to go to kilojoules so that I can add it to this number here. Yes, ladies. Okay, 1 second. I will get that for you. I will, yeah, I'll write it down. You guys, pull out this sheet here, read over this for a second. Nuclear chemistry from me. She gave specific. Okay, I'm hoping I have one. I think I do. If not, I'll just, I can find things. I should have nuclear. Yes, let's review of nuclear chem. Perfect. This video is fairly straightforward. There are probably a couple pieces that you can skip, but I will give you this on a shorter link. Okay. Can you take a picture of this? Do you have your phone with you, or write this link down? And let me know if you guys have any more questions.
Okay. Thank you.
Thank you. We have to wait until the end of November.
So there's one higher that you can't really do.
Not really. We still don't have anybody hired. Because, you know, like, there's no teachers in November. I mean, October, most of them are hired, or most of them are not good, so we don't hire them. That's why they don't have a job in October, right? Okay, so I'm glad you guys looked over that. Heat transfer 1 through 6. Anything I need to do there? Speak now for which piece? That was, I think that was my honors chem problem set from last year. Okay, some of it is incredibly similar. Hey, bye. All right, so you guys want to watch nuclear chem? It's here. On your time. Let's go through this problem here, and then we have another one that's kind of related to your life. Because tomorrow, what we're going to do is we're going to be doing a challenge on who can create the best hand warmer. Dun dun dun. Ooh. All right. So you need to know a bit more about how to measure the heat transfer between two different objects, like your hand and a hand warmer. It's going to be that time of year, so you know, start making energy for. Oh gosh. You guys know we turned back the clock on
this
Sunday.
weekend. Oh,
Yeah, maybe an hour.
No.
Wait, is it first? I think so.
Is that your birthday?
Get an extra hour sleep. What? All I wanted. Yeah. Are there limitations on how to make hammer? Yes. We'll talk about it.
Make a head warmer.
I could. I don't. Yeah, there are limitations because if you burn somebody, then you get sued. So we have to have like limits on chemicals so that they don't make too much energy. There was a rumor going on over at Jam Rob that somebody here in a chemistry lab got so burnt they were in ICU.
What?
I was like, the teacher texted me.
In the AP Chem
How did they find out?
Class. No, they just said chemistry in general. I was like, I think I would know this. I teach predominantly, and they haven't even done a lab in like a week and a half. There's no other chemistry. Don't
me and the AP Chem kids at JM will like help each other out sometimes. So it's like they don't know.
Well, no, she texted me. I was like, I would know this. I would know this. No, this is not wrong. This rumor is not true. Anyway, okay. Back here. Here's data. If 40 grams of water at 54 degrees C is added to 60 grams of water at 20 degrees C, what is the temperature after mixing? Blah 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 blah. That's not the one I want to do. Hold on. Is this what I want to do? No, you guys did one similar to this on your homework. No, this was temperature at the end. No, this is what I want to do. Ready? Write down. I have two. I was meaning you guys did one in here, but not this one. You guys have two. This can be extra problems in notes. Yeah, this will kind of be at the beginning of notes. Because as we go through notes, you're going to kind of tell me what you get, so I don't have to go over all of it. We'll just practice it. Okay, so 40 grams of water, 54 degrees C, 60 grams of water, 20 degrees C. What is the temperature after mixing? How would you set this up? This is not a specific method. This is just like, can you math? Can you math?
I don't know, can I?
What formula comes to mind? Okay, MCAT equals MCAT, right? So we have two masses. We have two initial temperatures. We have C for water, 4.18 joules per gram degree C. What do we not have?
The delta T, because we don't have the final temperature.
Yeah, we don't have total delta T, but we have T initial, right? But we don't have T final.
Right.
So you would set MCAT equals MCAT, everything known except for T final. And I actually would not put delta T. I would put like T final minus T initial, MC, and then MC, T final minus T initial. So what we don't know are these T finals, one of which is negative, right? So one of these, which water do you think is going to be losing energy?
40 grams or 50.
Right, the hotter one is going to flow to the colder one, or the lack of heat. So I want to show you how to basically set this up. I just wanted to kind of pose you the question, see if you figure out how to solve it, because I think you guys can do the math fairly easily. So this is going to be the 54 gram sample. This is going to be the 60 gram sample. This one is going to lose the energy because it's warmer already. And so you can see, I know this says Kelvin, it means Celsius, okay? So you can see how the setup works, mass, C. So what can you automatically kind of do to simplify your math? Right, so cancel the C's because they're going to be the same when you divide on both sides. So then really you're just working with 40 grams, 60 grams, and then your delta T's. But your delta T's, you know one of the temperatures, so you should be plugging that in. This one did not cancel. We try to simplify our math as best as we can. So whenever you're looking for your T finals, it just is going to be some FOILing and some subtracting, and then you're going to find what T final is. That process kind of makes sense. Like that's really the only equation you can use because that's the only thing with T final in it, right? And from there, you can just see the manipulation of math here. So your 40 grams and 60 grams get combined to be 40 divided by 60 is 0.667, and then T final minus 40 or 54, and then T final minus 20, and then you just have to distribute this 0.667, and then combine your like terms, your T finals, and then solve for T final be 33.6. In this case, does that make sense between our two temperatures? Which is it closer to? Because there's more of that, right? There's more of that lower mass. I mean, there's more mass of that lower temperature. So the average between them is going to be closer to the more massive one. You don't have to write down all the math. You should know just generally the process. Okay, shake your heads if you got the process. Okay, thank you. It's just solving for T final. Okay, this one, what's up? Can I go back? Okay, never mind. This one. This is the one that's going to be similar to what you might be expected to do in the lab. Okay? So what we're going to be using are these nice coffee cup calorimeters, styrofoam cups. But the coffee cup calorimeter, we know it's a good insulator, but it's still a calorimeter. It still can absorb a little bit of heat. And we need to account for that heat because what's releasing that heat? The substance, the system, the chemicals, the hand warmer, whatever you're making, right? So we have to be able to account for all the heat gained or lost. So in this, well, yeah, this is similar. I'll go back to example 1 in a second. But using the same final, or using the final temperature we just got was 33.6. Instead, it only reached 31 degrees C. So what happened to the rest of the energy? It's absorbed by the coffee cup calorimeter, right? So it's instead of going to 33.6, it only goes to 31. So the lower temperature final will be due to the heat that's transferred to the calorimeter instead of to the cooler water. So it's basically a cup. You pour hot water in, you pour cold water in. The water comes to a final temperature, but it's actually not going as high as it should be. What will be the heat capacity of the calorimeter? So what variable is it actually looking for here? What kind of C?
Big C.
Big C, okay. So the question is really what's big C? Well, what equation comes to mind if you know you have to calculate big C?
Q equals big C cat.
Okay, Q equals big C cat. Okay, so then if you wanted to solve for big C, what would you be doing to manipulate this equation?
Divide by delta T.
So you would find Q of the calorimeter. You find Q of the calorimeter, and you divide by delta T to get C. You guys with me so far? Okay, so if you know you have to get to the Q of the calorimeter is the difference in energy that should have been absorbed by the water, by the water or transferred between the waters, but instead it's absorbed by the calorimeter. So we need to figure out the difference in the hot water energy and the cold water energy to see how much actually was transferred, that was transferred to the coffee cup. So this is your basic setup. You know how much heat is lost if you calculate it. You know how much heat was gained if you calculate it. There's going to be a difference, and that difference is accounted for by the coffee cup. So how would you get heat lost from the hot water? And remember, we have all that data, that information available to us from the previous question. What variable is this looking for? Q, right? So how would you get Q? MCAT, right? And the M was 6, which was the hotter one? 40 gram one, right?
Yeah.
40 grams times C. Delta T is actually known in this case. We know the whole shebang. We know it started off at 54 degrees C in example 1, and it ends at 31, so we know delta T. And then same thing for this one, but this is going to be which mass?
60.
Right, this was the 40 gram one at a hotter temperature. This one is Q equals MCAT with the 60 gram sample at a lower temperature. It started out at some other temperature. I have it right here for you, so that's why I'm not flipping back. So once we get heat gained by the calorimeter, the difference in heat, to find the specific heat capacity, to find the heat capacity, we just are going to divide by the overall delta T. So here's the math. So we have delta T, the final temperature minus the initial temperature, 40 grams delta, or our C value. Subtract T final and a T initial. This was information given to us previously, 60 grams, and this information about the specific heat of water. So when you calculate heat, it's 1.09 times 10 to the third joules, and that's the heat absorbed by the calorimeter. You'll have to do this in your lab, so make sure you're comfortable with. There's multiple pieces of data, and you put them in the correct spot. Okay, so then how much did the water? What was the temperature change of the water? You guys see it went from 54 to 31 here, 20 to 31 here. So if we're talking about the heat transfer, how much heat was actually transferred, or temperature change was transferred to the cold water? What was the temperature change of the cold water? 11 degrees Celsius. So the temperature of the cold water is the energy that's transferred from hot to cold, right? Well, truly, all of the heat that's lost should be transferred to the cold water, but only a portion of it was. A portion that allowed for the water to increase by 11 degrees C. The rest of the energy went to the cup. So that energy, that temperature change is the delta T that we're looking for to plug in up here. So it's the temperature that cold water changes by. So math, Q is that, Q the calorimeter, and then 11 degrees C is our temperature change. So then Q cal, we're in a space here. You would just do 1.09 times 10 to the third joules divided by 11 degrees C, which is Q over delta T, and that gives us our heat capacity of the calorimeter to be 98.7 joules per per delta C, degree C. So in this case, our coffee cup's not really absorbing, it's not even absorbing a whole kilojoule, which is great. You'd expect styrofoam cups to absorb very little heat. So like between 1 and 100 joules is good. If you have a coffee cup that absorbs 200, 300 joules, it's more conductive, and so your hand will get really hot, right? So you can imagine what kind of substances would allow for more heat to transfer. Metals, right? So that's why a lot of times like ceramic and metal coffee cups, they get warm really quick. That's why gas stations sell the other ones. You with me? So like edge the world here. Okay. So as I go through some of the Hess law stuff, tell me what you get so we can move on to practice. There's just some background information I want to make sure you're aware of. This we talked about already. Okay, so this is something that we mentioned already. We talked about constant pressure constant pressure calorimeters, constant volume calorimeters. What was the constant volume calorimeter? What was it called? It's a metal jar, bomb calorimeter, right? And that's where they combust things in. They'll say, oh, this amount of heat was transferred to the calorimeter, and that one's probably going to be a metal kind of container, and that one will have a lot of heat transferred to it. And if you want to find delta H from it, then you would actually calculate Q and divide it by moles, combust it, and you're good. Generally, we will be using constant pressure ones. So the constant pressures, this is like a proof of why the enthalpy, this is the definition of enthalpy. You'll notice there are no deltas over here. Why does the definition of enthalpy allow for us to just assume off the bat that enthalpy and heat are the same for coffee cup calorimeters or the constant pressure ones? It's a proof. You can just take it for what it's worth, but I need you to know this. I need you to know that delta H is equal to Q for constant pressure calorimeters. And that allows our calculations to be much simpler. So much simpler. We're always looking for simplicity if we possibly can. And this makes sense because if pressure is constant, and in this case, change in volume is usually minimal, then we approximate that P delta V to be approximately 0. So then that allows us to kind of just assume Q is equal to delta H. But delta H is generally measured in kilojoules, per mole, and then Q is generally in joules or kilojoules. So we have to do a little manipulation of the data, but other than that, this is just some like assumptions we make in chemistry to make our calculations easier. There's not a whole lot else here to write down, just to know that those are approximately the same. So whenever you're writing down, the last video you guys watched was the formation video, and this is a very specific, this is a very, very specific term that is used. So anytime you're asked to use or to calculate the standard enthalpy of formation, it means, I'll go back up to this other stuff in a second, it means that you're forming 1 mole of that compound, you saw that in the video, from its elements. So you have to break down whatever the compound is into individual elements, and you have to write the elements as they would exist at room temperature. And room temperature for us is 25 degrees C. So this is all really, really important stuff. You may have written down some of it yesterday, but if you have your instrument yesterday, just add to it. I don't have that on your extra notes at all. So things that are written at standard conditions are calculations that are done at standard conditions. The way we denote it so everybody knows, so we put that little knot at the top. It's this little degree symbol basically. So if I say like delta H formation knot, it means at standard conditions. And those standard conditions are just experimental conditions that kind of ensure that all of our calculations are equivalent across international experimental guidelines. So we don't say STP here because STP is what temperature? Right, so this would be 0 degrees Celsius, right? We're talking room temperature. We're talking about like laboratory conditions. Generally you're not going to be doing conditions at like 0 degrees Celsius. You're going to be doing experiments. You're going to be doing experiments at normal temperature. And then if we're under pressure, we're going to call it 1 atmosphere. And if we're using solutions, like 2 solutions put together, we would generally be using 1 molar solutions. So when I say standard conditions, these are the conditions I mean. And if standard conditions are present, we get to use this lovely table of values in the back of your book. Does anybody have their textbook with them? Nay? Should have told you to bring them. Appendix 4. You see these little numbers? I'm sure you can. Yeah? Look at all those little numbers. This is a table you will have access to. If on the test, if I want to give you values, I'll probably just make my own table and I'll put it at the top of the test and go use these values anytime you need to. But in the book it says substance, so like you want to look at nickel 2 sulfide. The delta H of formation for nickel 2 sulfide is negative 82 kilojoules per mole. Okay, you can look up any substance practically and find its delta H of formation, and that would be the energy that's released whenever 1 mole of that substance is formed, or absorbed. It just depends. Most of the time they're released. Most of the time they're negative. So there's a table that you have access to. Okay, so on your, I'll come back to this in a second. On this paper, you have this little sheet right here. Yeah, we're going to go through some of those equations because we have to be able to write thermochemical equations. Thermochemical equations are just BCEs with a delta H at the end, or energy involved somehow to indicate the thermochemical nature of the equation. These other deltas here, delta S and delta G, those are thermodynamic variables. So this one's enthalpy, this one's entropy, and this one's Gibbs free energy. Does anybody remember delta S from last year honors chem? Entropy, a measurement of disorder. Maybe. Okay. Delta H you definitely have seen numerous times, but the other two we're going to talk about later in this unit. Okay, so this right here is a thermochemical equation. It basically has reactant yield products, and then you have the delta H indicated at the very end of the BCE. Whenever you form 1 mole of product, that sometimes means you can't make or have a full mole of every reactant. So you are allowed to use fractions on these BCEs. Only in thermochemical ones can you have fractional coefficients. Okay? So if I wanted you, before I even do this question here, if I wanted you to form 1 mole of sodium chloride, so I wanted you to tell me the delta H of formation of 1 mole of sodium chloride. You need to mention the state of that matter and then the elements that are used to make it at their standard state. So this is an ionic salt. What generally is the state of matter here?
Solid.
Solid. Ionics are solid. What 2 elements are used to make it up?
Sodium and chlorine.
Okay, but how do I write sodium and how do I write chlorine? At standard states and the normal kind of everyday forms.
Sodium solid.
Sodium solid and
CO2 gas.
Cl2 gas. Because it has to be diatomic, because chlorine doesn't exist as a singleton, it exists as a diatomic molecule. So then how would I balance this?
1/2 on chlorine.
And that's where the fractional coefficients have to come in, because you are not allowed to make more than 1 mole here. If not, you would double. If you double this to be 2 moles, you have to double the delta H as well. But the definition of formation is formation of 1 mole, so don't stray from it. So I could look that up in the book. I don't remember off the top of my head, but it's probably like negative 500 kilojoules per mole. Because usually forming ionic salts is very, very, very stabilizing. So whenever you're stable, you have lower energy. So why does that make sense in how I've written it here? So this is more stable than these two, because when these reacted to form this, what happened?
Energy was released.
A ton of energy was released, right? And that means that the product itself is actually very stable. So if you're in your like energetic, high caffeinated, high sugar self, then you're like kind of crazy, not very stable. But if you're calm, chillaxing, and AP chemistry, in some more stable, happy place. Okay. So let's look at how we can use this thermochemical equation or one like it to solve a problem for like heat energy or heat involved. So when 58 grams of methane burns, that much heat is released. Write a thermochemical equation for this reaction. Let's write out the thermochemical equation first, and then we'll find delta H. So what's the reaction?
CH4
Is it balanced? So I need 2 here and 2 on there too. And then these need states. Anytime you have thermochemical, you need to write the states as best you can. So generally the rule of thumb is anything that is butane and lower, so C1, 2, 3, those are all going to be gaseous because they're really light molecules. So this methane is going to be a gas. You know oxygen is a gas. You know CO2 is a gas. And then when it combusts, generally water will vaporize. But if you put liquid or gas there, I just need to check what you wrote so I could check your calculations, because liquid water and gaseous water have different delta H's because they have different amounts of energy that are used to create them. Okay, so if that's our BCE, how would I get delta H?
Get some moles.
Get some moles of methane and then do what? Huh? I'll get some moles first. Okay. A smaller mass of methane.
16.
So, what is that? 0.4 or something? You know, with all your calculators and stuff.
3625.
Okay, that's moles. Now how do I get the delta H from the given information?
Under the 30
Okay, so 320 kilojoules of heat that is released. So what do I need to put here? A negative, because it's exothermic. That amount of heat is released per this many moles that combusted. So what is our energy of our energy transferred here or lost? 320 divided by 0.3625. Anybody?
882.76.
Oh, accidentally multiplied. Say it again.
Negative 882.76.
83 then. Cool. Joules, not kilojoules. Negative 883 joules per mole.
That's cool.
It is kilojoules, thank you. Alright, so this delta H would go right there. Negative 883 kilojoules per mole. So the thermochemical equation just means that a lot of times you're given data, and the data must be used to find delta H before you finalize your BCE. Okie dokie? So if I know this information, that means that per 1 mole of methane combusted, that amount of energy would be released. But I had obviously a lot less than a mole, so that's why only 320 kilojoules was released and not 883. So it's proportional. It can this can be used as a conversion factor as well, anytime you need to, in converting from like moles reacted or moles combusted to energy evolved. That's what the next one is. So calculate the amount of heat produced when 25.1 grams of methane react. We already know the delta H, and this is, what is this per again? So I'm going to say 1 mole of methane, because it actually relates to the BCE. It's stoichiometrically related to the BCE. So this amount of heat's related to 1 mole of methane, to 2 moles of oxygen, to 1 mole of carbon dioxide, and to 2 moles of water. So this could be used in any method, just according to the BCE coefficients. So what do I start with?
25.1 grams of
Okay, and then, so methane is 16 grams per mole. Okay, and then,
negative 883 kilojoules over 1 mole.
and this would give you, this is 1 mole of methane, and this would give you the amount of energy that's released, 5 grams, and you should know it's going to be more than 883, because this is a lot more than 1 mole of methane according to the molar mass. So that's going to be like
1385.
negative, so 1385 kilojoules, and I'm just going to say that much is released. So if you say the word released, you don't have to write the negative, because they mean the same thing. Or if you just put negative 1385 and didn't put released, it's understood that you mean it's exothermic. Easy so far? Not a lot of new stuff, it's just manipulating data. Okay, so now I want you to write the formation equations for, I'll come back to this in a second, for this one first. You guys have this on your paper. So the standard enthalpy formation for silver nitrate, and then I'll look up values for you in the book. You can tell me what you're writing to if you want. So what's your product?
Silver nitrate.
So just 1 mole of silver nitrate, okay. And what are the reactants?
Solid silver.
No, silver.
Silver.
And how do I write nitrogen? And how do I write oxygen? You have to write it from its elements, not its ionic compound or ions. It would be from its elements. So silver would be a solid, nitrogen would be a gas, oxygen would be a gas, silver nitrate would be a solid because it's ionic. Anything that's ionic is going to be solid unless it's in solution. So balance them.
3 halves on the oxygen and 1 half on the nitrogen.
Right. So if you have a 3 here and you have 2, it's because it's diatomic. You have a 2 here. If you just multiply by that number over 2, it will always cancel and give you what you want. So 3 halves here, and then 1 nitrogen. So you need 1 half nitrogen here, and that's your BCE, except for the delta H. Delta H of formation is what was asked for, and this is at standard conditions because it says standard enthalpy of formation. So standard means right this little not symbol here, and this value, whenever you look it up in the book, is I have notes someplace. There we go. Negative 124. Oh, does it? Thanks, right there. Kilojoules. Okay, so you have your, thank you. You have your original, and this is just the definition of standard enthalpy of formation from its elements. Okay, so then I may not write out the rest of these, but I want you to tell me how you would write them. So if I say standard enthalpy of combustion, what would you be doing with ethanol? Right, just combusting with oxygen, making CH2 and H2O. This is not enthalpy of formation one, so it does not involve just elements, it involves a reaction in this case. And this one is negative because pretty much, no, every single combustion reaction is going to be exothermic. Okay, next two, let's start here. I want you to write out this one, vaporization of water. So how would I write that BC? It's kind of, it's not really a chemical equation, it's more of a phase change. Right. H2O gas, and then this is enthalpy of vaporization, which is 43.99, and why is it positive? Right, the liquid water requires energy to overcome those IMFs, those intermolecular forces, hydrogen bonds, so that they can totally separate to form the water vapor. But what is does the molecular structure of this change at all? No, there are no chemicals bond broken, there are no chemical bonds formed, it's just separation of the molecules themselves. Okay, for this one up here, solution process, you actually have to show the solution process by making it go into solution, so aqueous solution. So if you have solution of sodium, or if you're looking for the standard enthalpy of solution for sodium hydroxide, you start with sodium hydroxide. What's the state of matter most likely? Solid. It's a powder. It's something that's like in pellet form, okay? All ionic substances are solids. And then whenever you add water, and you can add water above the arrow, then, because it's going into solution, what happens to sodium hydroxide? Mm-hmm. It actually ionizes as well, right? And right. So, and this is only because it's a strong base that it's able to ionize. So that right there is going to be how we write out the enthalpy of solution, and then delta H of solution, standard conditions in this case is negative 44.57. So that's just these, they have very specific ways of writing it, and you can easily get something wrong if you don't think about what the solution process is and so forth. So this is solution of a ionic compound, because ionic compounds generally will ionize in solution here. If it's for a covalent compound, so like give me a covalent compound that dissolves. Sugar, right? So any carbohydrate generally. And so we don't call that enthalpy of solution because it doesn't really go into solution. We call it enthalpy of hydration. So if I ever ask for enthalpy of hydration, and let's just do it for glucose, you write C6H12O6, and that at room temperature is a solid. You've seen glucose, you've seen sucrose, you've seen a lot of carbohydrates, they're solids. When it goes into water, it's called enthalpy of hydration, and it does not dissolve, right? I mean, it does not ionize, it dissolves. Dissolves is our Leibniz term. And we just write it simply with aqueous like this to say that it's in solution. And so hydration means that water molecules surround it. So like if this was a molecule of of glucose, water would just be hanging out around it so that it was dissolved in solution. But nothing really happens chemically. Okay. How much more do we need to do here? Not a lot. So let's go to a practice one. Let's go to, oh, this is on your notes. Sorry, you guys have your notes out. This is what I was telling you earlier that we just talked about where the delta H's are, how they can be calculated in multiple ways. You know how to do this one. You got this. You know how to, if I give you data, you know how to find Q, you know how to find moles, you divide. So I'm not going over that one again. And that one's like a data-based question. If I ask for you to get delta H and I don't give you data, generally I'll be giving you different information. I'll give you things like reactions, or I'll give you a book with these standard enthalpy formation values. And that's it. They're like table of values, not really data from a lab. So if you have access to the standard enthalpy formation table, huge table, this is what you will use. This is called Hess's Law 2, but I just call it H products minus H reactants too, so it's very clear on which type of Hess's Law we're talking about. And did you guys glean from yesterday's video that free elements always have a delta H of formation of 0? So give me a free element. Give me a example.
Chlorine gas.
Chlorine gas would have a delta HF of 0. What else? O2. What else?
Sodium solid.
Sodium solid. Anything that's just a free element or a diatomic molecule would have a 0 delta H of formation. So if I wanted you to write out how to calculate the delta H of this reaction here, this is a combustion of ammonia reaction, how would you set this up and what values do you already know? Setting it up like this. Whenever you're ready. Delta H reactions equal to 4 times what? The delta H formation for what compound? Products, right? Minus reactants. So you're doing these first, right? You have to do products first. So this would be delta H, a formation of nitrogen dioxide, okay? Plus 6 times delta H of formation of water, liquid, and that's a specific point because liquid water and gaseous water have different delta H values. So you would find these values in the book, right? And I could put them up here for you, but I'm just telling you, you can find them in the book. That's your H of products, and you'll see a summation, so I added them, and it's N, which means number of moles, so I had to look at 4 and 6 to account for the number of moles. Then subtract what? Times delta H of formation of NH3, gaseous, and plus 0. And you can say plus 7 times 0 to be like, hey, I know I have to use the 7, but it's plus 0 because this is a pure element. Okay, and then all you would do is just multiply and add, subtract this thing, and you get delta H of reaction. So this equation is on your reference sheet. You will use it a lot. Okay, and just don't forget that you have to use products minus reactants. Yeah.
So does it matter if we write 7 times 0 or just 0?
If you just put 0, it's fine. But if I generally in my FRPs that I do, I'll do 7 times 0 because sometimes they'll give you a point for that. Why? Don't know. 7 times 0 is 0. It's 0. Okay, and then this we'll do a practice with the delta H products minus delta H reactions in a second. This is the Hess's law of summation. It looks like a lot of details, but basically if you have BCEs, some other things that you want in your target equation are going to be on the reactant side, some of them are going to be on the product side. And you have to manipulate the BCEs by flipping them or by multiplying them by coefficients to get what you want in the target equation. And then from there, if whatever you do to the BCEs, you got to do to the delta H's because they are equivalent based off the stoichiometric relationship. Then you add them together and you get the final. But this is on your paper, so I'm going to show you an example of this first. Oops. Okay, so here's my example. This is my target equation. Do you want to write down your target equation? And generally I write it down at the bottom of my paper because that's usually where I do all this manipulation and then I get to my final BC at the end. So write down your target. This is rocket fuel. Boron plus hydrogen gas yields diboron hexahydride, or no, hydride? Yeah, hydride. diborane, actually, synthesis of diborane rocket fuel. Okay, so if you know your target BCE, generally what I do, and I'm going to rewriting these are always going to be given to you with their delta H values assumed as well. And, just need more space. If I know that I want this, I always write this at the bottom, 2B solid plus 3H2 gas yields B2H6 gas. Okay. So I need to hunt for the things that are reactants and hunt for the things that are products. I'll look for the B first. Well, I have 2B here. I don't have B's singletons anywhere by themselves, so this reaction is going to stay as it's written. I will not flip it. So I'm going to write that first. 2B plus 3 halves O2 yields B2O3. And this one is solid, gas, and solid. Delta H is going to stay the same for now, negative 1,273. All right, and so usually if I know I want to keep it, I put a little box around it because I remember that I need it down there. But I already know that I do not need any oxygens, and I do not need this B2O3 thing. So I know that I want to cancel out these two reactants and products. So if I want to cancel B2O3, which equation would allow me to do that? Oh, what do I need to do to it? Flip it. Right, so if I flip the reaction, I flip the sign, so I go to a positive delta H versus a negative. So I'm going to write this one here, B2O3 plus 3H2O liquid yields B2H6 plus 3O2, and this is now going to be positive 2O3. Okay, so then now I want to go ahead and cancel before I move on, because I want to make sure I don't need to multiply this by any multiplier. So if I have a 1 B2O3, I have a 1 B2O3, those actually cancel automatically. I don't need a multiplier. So I'm just going to show that for you here, but you don't have to cancel it till the end unless you want to. Nothing else really cancels except for some of these oxygens, but I know that I'm going to need how many more oxygens on the reactant side to cancel? Another 1.5, right? So that's where I'm going to wait and cancel that towards the end. Okay, so this last equation here is the only one I've not used. So if I want to use this, and I see that I've got water on the reactant side, and I don't have water on the reactant side in the end, I know I have to cancel water, right? Yes? You see it's not present in the end, so I need to cancel it. So I'm going to leave this reaction as written, because it's going to have water on the product side, and it's going to have this oxygen on the reactant side to help balance out the 3 oxygens that are here and the lack of 3 oxygens that are over here. So I write this as is, and then you guys are going to tell me what to do with it in terms of manipulation. Y times 3. Yes, so you need 3 H2s in the end. So I already know I'm going to multiply this whole thing by 3. So what do I do to the delta H? Also multiply by 3. So that's going to be 3 times negative 286 as our delta H. So then we just want to make sure, and it always works out, unless we've done something horribly wrong, but just make sure everything cancels. So we already got our B2O3s canceling. We've got 3 waters here, canceling with 3 times 1, so 3 waters here. We have 1/2 oxygens plus another 1.5 oxygens, which equals 3 oxygens. So all of our oxygens cancel, and then what's left? You see the H2s left? There's 3 of them, as we stated here we needed. And then there's what else left? The B2H6 here, and there's 1 of them here. So we're good. The 3 things we needed stayed, and then what would we do to find that delta H? Just add them up. So somebody add those for me, and I'll verify. That's a lot of energy that's released whenever this rocket fuel is synthesized. But that's our delta H. Delta H of reaction or combustion or synthesis actually. Is this formation? Yeah, because it's from its reactant, so this is delta H of formation. Okay, so those are 2 of the types that you'll need to know for Hess's law. The last thing I really want to talk to you about is that last bit I just skipped on you. Delta, or the bond dissociation energies. We kind of just went over all that. Bond dissociation energies. Oh, okay. So thinking about bonds, okay? You got a covalent bond in front of you. you want to break it. Do you think you're going to put energy into that process, or do you think you're going to have to somehow relieve energy to break something? I'm going to have to karate chop it, okay? That's how I remembered it since I was like 15. How do I break a bond? I karate chop it, and that is not easy. You have to put energy into that process, right? Who karate chops? You put energy into it. Okay, you will be doing this. So remember, breaking bonds is an endothermic process that requires energy. So then, forming bonds is exothermic, because when two things come together, they're actually a lot more stable than they were independently. So two independent things are high energy. When they come together, they're actually more stable. And when you're more stable, you're in a happy place, so you have lower energy. So what happened to all the other energy? It was released. So I like to think of that as a happy marriage. When they come together, bonding forming is exothermic. Sorry, did I switch these on this side? Yeah, they're switched. Okay, so this is exothermic. Okay, so this is what happens. Two entities, when they're together, they're happy. When you separate them, it required energy to do that. That's what's a positive amount of energy. And then vice versa, bond formation. They're unhappy, they're high energy, they're stressed out. They come together, they're happy, they release energy, negative. But these values, you see the positive 163 and then a negative 163? They're the same value, but opposite directions, because what happened to the reaction? We flipped the reaction. Okay, so tell me, you know this now. This was on your notes from yesterday. Kind of? You drew out structures. Okay, write this down if you don't have it. This one looks a little different. This is using bond dissociation energies. Guess what? There's a whole table on page, oh darn, I can't remember the page number. I'll look in the book for you guys. This is another table of information given to you. But all of the values in the table are positive. They're all positive because of the way bond dissociation energies are measured. Whenever they measure bond dissociation energies, all they do is they break bonds. And would you just tell me that what kind of process that was, breaking bonds? Right, endothermic, it requires energy. So that's how, they can't really measure the bond formation, they can measure bond breaking. So they establish everything's an endothermic value. So then how do we account for the whole exothermic nature of forming bonds? We put this negative in between them. So it's the bond dissociation energy of reactants is positive, and this energy here, when I say bond dissociation energy of reactants, this means bonds broken. Because the reactant bonds are broken, right? They have to be broken so they can rearrange. And the energy of the bond dissociation energy of the products, technically in the book, are positive. But when we say subtract, that means we're accounting for the whole exothermic process of bond formation. So this would be bonds formed. So what's different about this reaction, or this equation than the previous one? Right, reactants are first, products are second, right? If you can't remember that, I think you can at least remember bonds broken minus bonds formed, and that's what I always default to because it's in alphabetical order. Maybe you can remember it that way. Broken is first and then formed are second. So reactants are broken, bonds that are formed are products. Okay, so then I have like one example of this to make sure we're all clear on how to do this one. So it means you have to draw Lewis structures. So you got to remember how to draw some Lewis structures for me. For this. What is this guy? What is it?
Methane. No, methane.
This is C, two C's, right? Ethene. Whew, ethene. So how does ethene look? Draw it out. I told you there were the double bond is. So draw it out. C, double bond, C, with H's. Okay. Plus, guess what? What?
Plus H.
H bonded to H. Single bond yields.
C.
That's nothing. No,
H.
Ethane. C bonded to C with a single bond surrounded by 3 H's on each side.
Yeah.
Okay? You literally have to draw out every bond because it's called bond dissociation energy. And if you don't know all the bonds, then you're not going to get all the bonds broken and bonds formed. All right, so now your job is to account for bonds broken minus bonds formed. And I always just write them out just like the equation says to, but I write out the bonds themselves. So we have one C double bond C that is going to be broken. And see, I'm starting with reactants on this side. And then how many CH bonds are going to be broken? So plus 4 CH bonds that are broken. And what else is broken? One H to H bond. H to H bond. So I actually write out my bonds so I can look them up in a table, because the table looks exactly like this. And I'll show you what it looks like in a second. Minus what? So 1 CC bond and
6 CH.
6 CH bonds. So what do you notice that we could simplify if we wanted to?
Yeah, C to H.
The CHs, right? So I have 4 CH bonds here and I have 6 here. So what am I really doing in my math here?
Subtracting 2 CH.
So this technically goes away because you're subtracting 6. So this would be subtracting 2. Subtracting slash adding. But you don't have to do that. Don't worry about simplifying. If you just want to plug, you're good here. So then what does the table look like? I think it's in chapter 16 for those of you who want to write that down. You can also just Google no, it's not in chapter 16. Chapter 17? No, it's chapter 6 still. I'm lying to you. I hope I'm lying to you. No, I'll find it. It's not, I know the Zoomed book, but I don't know this book, which chapter it is on. But there's a table and they have exactly these formats on there, and you just pull the values, you plug them in, and you subtract. Okay? So you guys have about almost 30 minutes. I have more practice, but I want to make sure that you guys practice from your Hess's Law problem set and then from your enthalpy problem set. But the enthalpy problem set has some weird examples on there, so I want you to try them, and then we'll go from there tomorrow to make sure that you're comfortable with calculating. You guys have your Hess's Law problem set? You should have started it after you did it yesterday, but it's like 5 questions. 6 questions. Looks kind of like this, but you got it on one little half. It's like it's on copy number 2 to 3. Do I have the answers on there, Kevin? No? Okay, I'll write them up here. What's up, Chelsea? What's up? Question? Oh, sorry. Has anybody tried any of the Hess's Law problem set? What'd you get for number 1? Number 2? Negative 171.07 kilojoules per mole of reaction. Okay. Number 3? And you will be showing your BCEs and cancellations, right? You're not just going to have the answer. You need BCEs and cancellations. And multipliers and stuff like that, flipping it. I'll write up the rest of them. You guys keep working. Number 6 is a doozy if you want to start there.
I'll go there.
Get ready for it?
It's just easy.
You should be able to finish most of the problems though. They're not horrible.
She never got what she did and she got that run post, but it wasn't she never did.
What? What do you want? What? Yeah, you are multiple united, like they don't.
No, because we don't have more to do and we're gonna need more time. Clay, if you don't get it, let me know. I'm gonna have to because this one should take minutes. You should have started yesterday, so I know the videos of this took longer than I thought.